So far, we've been talking about the use of array or list as a data structure to implement collection ADT. In this video, we're going to talk about using linked list, specifically the singly linked list, not doubly linked list, as the underlying data structure to implement this ADT. The unsorted representation of this linked list, we will reuse various different design code from previous classes. The find method sets the Boolean is found or not found, plus the two pointers. And these pointers refer to both the location and the previous element. In the next slide, let's put both array-based and link-based find method side by side so you can see the difference between the two. On the left side, you have the array-based. Right side, you have link-based. Recall that from the array-based approach, you would iterate through every single element inside an unsorted array one at a time, starting with location 0 until you find it. So this is the O of n operation that calls for location plus plus, which is the index increment at every iteration as long as the target is not found. Once found, you set the found to be true. In a linked list approach, we have to start up with the location being at the head, which is a label to the beginning of your linked list. Like so. Recall your linked list ends with a null pointer, which terminates it. As long as your target is not found, you will continue to advance into the next node, and that is done by location equals location.next or get link. So this allows the pointer to hop from one node into next. So node hopping happens here. Notice that every time you hop onto the next node, you have to remember the previous location. Remember, in this context, every single one of these variables is a reference. So you have to remember the reference of the previous location before you hop onto the next. Let's say if the target is found right here and your previous is right here, your method find immediately returns with a found equals true along with the previous node and also the target node, which is the current location. Remember, previous, location, etc. These are global variables. So when your method returns, your calling function may do something with this t by adding a node after it, deleting it, or modifying it, or update. This is the reason why we must know the previous location of the node for inserting an extra node, for example, at the target location, or deleting the target. Let's look at how we remove an element in a link-based situation in the next slide. This is the remove method that returns a Boolean, whether the removal of this target is successful or not. And notice that this find method returns both previous and the current location of that target. That target is Lila. So we are going to remove this element Lila after find, which is O of n. Just to be on the safe side, if found is true, then we execute the set of the logic here. The first possibility is that your location is already at the head, meaning this linked list only has one element, and that element is the target, Lila. Therefore, you can remove Lila by advancing the head to head equals head.getLink, where it's next. The second possibility is in this else conditional, where your target is not the very first node, but somewhere in the middle or at the end of that list, in which case you will simply advance your previous node to locations next. And that is this dashed line right here, bypassing your target completely. This severs the connections you have between the two nodes surrounding Lila. Once done, you decrement the number of elements by 1. So this is how you remove a node at location, either when location is at the very beginning of the list or anywhere else inside the list. Once done, return found. If found is not true to begin with, then this remove simply just return found right away. Looking at the efficiency of your conditional clause here, there's no more iteration. Instead, you can treat each of these expression and statement as O of 1 times some constant, depending on how many steps you have here in your logic. So overall, your operation efficiency for remove is O of n, and that O of n comes from find. This is our high-level class diagram, UML, illustrating all of the components in use in the example so far. On the very top, we have collection interface with the set of transformers and observers. And we have collection in array and collection in linked list implementing it. For the linked collection class, we use a has_a linked list node. And this linked list node has a whole bunch of getters and setters. The sorted array collection is a little different than both the array collections and linked list collection in that the sorted collection implements comparable interface. This comparable interface is responsible for you to overwrite its compare to methods so that we can maintain the natural order of the elements inside the sorted array. Of course, your compare to defines how the order is established, depending on the underlying data type of your elements. In the next slide, let's compare collection implementations in terms of their efficiency.